So the rate of the reaction is simply the speed of the reaction, meaning how fast the reaction is going. And to measure the rate of the reaction, it is the change in the concentration of the reactants or the products, dividing it by the change of time required for the reaction to happen. The change in the concentration is the concentration at time t minus concentration at time 0, and the change in the time is the time at time t minus the time at time 0. In any chemical reaction, if you look at the reactants, they are going to react with each other, right? So we are expecting that the concentration of the reactants is going to decrease and the concentration of the product is going to increase. So this is in any reaction, reactants are going to react with each other. And as they react with each other, their concentration is going to start decreasing as the concentration of the product is going to increase. So let's have an example here. Calculate the average rate. So this is the equation for the rate. You don't have to memorize. We can put it on the cheat sheet. So calculate the average rate of the following reaction. We do have sodium water gives hydrogen and sodium hydroxide. A piece of solid sodium was put into pure water. So this is the reaction. These are your reactants in there. So sodium is going to start reacting with water, right? So the concentration of sodium is going to start decreasing. It's going to react with water, and now you're going to have more concentration of the sodium hydroxide and the hydrogen. So all the sodium has reacted. You can see that in the products, there is no sodium in there. There's no sodium in there. This means that all the sodium solid has been reacted. So we say that the reaction has gone to completion in here because there is no reactants that appear on the product side. After 8 seconds, so this is the time, and the concentration of the sodium hydroxide was found to be 0.013 molar. So it's telling me that the concentration at time t is this much. The concentration of the sodium hydroxide at time 0 was 0 because at time 0 we had sodium. We did not have sodium hydroxide. Okay, so the concentration there is going to be 1.3 times 10 to the minus 3 molar minus the concentration is going to be 0. This is the rate of the reaction. So when we say the rate of the reaction, it's how fast the reaction is in order to get to the product. So you're going to look at the concentration of the product in there versus it took 8 seconds in order to reach the product, which is the sodium hydroxide. So it took 8 seconds for all the sodium to react to make sodium hydroxide. So that is my final time, and my initial time is going to be 0. So my answer is going to be 2 times 10 to the minus 4, and this is molar per second. The time is always measured in seconds, and the concentration is measured in molar, and this is the units for the rate of the reaction. So how does a reaction happen? To explain how a reaction is happening, there are a series of steps that the reaction undergoes, and these steps we call them reaction mechanism. So a reaction mechanism explains how bonds are broken and how bonds are formed. This is what a reaction mechanism is. It's basically the number of processes that must take place for the reaction to happen. And for the reaction to happen, we mean by that for the product to be formed. So for the product to form, there should be bonds broken and bonds formed. So how can bonds be broken and how can bonds be formed? There are 3 assumptions, you guys. And those 3 assumptions are important to explain how a reaction happens and how the reaction mechanism goes to form the product. The first thing is the collision. This is the first thing. I mean, for the reactants to react with each other, they have to be close to each other, right? So once they become close to each other, collision must happen. So once they become close to each other, collision must happen. So collision is necessary for the reaction, and during the collision, some bonds are broken. and atoms are exchanged, as you can see in there, and new bonds are formed. So in order for a reaction to happen, the reactants need to be in a close proximity to each other. So once they are in a close proximity to each other, collision is going to start happening, and bonds are going to be broken, and atoms are going to be exchanged, and new bonds are going to be formed. So you can see here that I'm breaking the bond between AX, and I'm breaking the bond between B and Y. And then A and Y now are being formed. So this is now a new bond that is formed. So bonds are broken, bonds formed. And then a new bond between B and X is going to form. The second assumption is the energy. Reactant particles, they should collide. I mean, we said that collision is going to happen between reactants in there, right? But the collision requires minimum energy. So the collision should happen with sufficient energy, which we call minimum energy. So that sufficient energy, it's going to be minimum energy. And that minimum energy is required to break and form new bonds. We all know that at temperature absolute zero, which this temperature cannot be achieved, this is 0 Kelvin, there is no life. So the bonds stop vibrating. So anything that we're assuming in here, it's going to be at temperature, of course, above absolute zero, because absolute zero temperature is not achievable. So at all temperatures above absolute zero, we are expecting that bonds are vibrating, okay? So in a molecule, so this is a molecule in here, bonds are vibrating. Depending on the vibrating frequency in there, if the bonds are vibrating just a little bit, then this is going to be low internal energy. If bonds are vibrating strongly, this is going to be high internal energy. And bonds, they need to vibrate, because when they vibrate, this means that they are stretching. And as they stretch, the bonds are going to be broken. So once they reach minimum energy in vibration, this means that once they stretch at a minimum energy in there, bonds are going to break. So the internal energy has to be high enough so that bonds vibrate, bonds stretch, and then the bond is going to break. So the internal energy normally can be increased by collision. This can result in an increase in the vibrational amplitude, which increases the chance for the bond to break. And this happens by achieving a minimum internal energy for the bond. The third assumption is that particles, they need to collide at the correct orientation, so that they can do a reaction and they can bond with each other. Okay, so this is the last assumption. There is a short video in here that you can watch with this link if you want, about the collision and the bond formation in chemical reactions. Now, to go over chemical reactions and how fast they happen, we need to explain the energy diagram and the activation energy. So to start, the term stable requires the use of minimum amount of energy. So whenever we talk about stability, this means that we're talking about low consumption of energy. And if we change that into stable reactions, so the term stable reactions, it means that the energy that is required for the reaction to happen is low at a normal temperature. So when we say a reaction is stable, this means that the amount of heat that is produced, the amount of energy that is produced should be low, okay? Should be low. This is what a stable reaction is. So a stable reaction produces low amount of heat. The term activation energy deals with the speed of the reaction. how fast the reaction is. This is what an activation energy. So the small amount of outside energy which is needed to start a reaction. And we need the activation energy to be a low activation energy for the reaction to happen fast. Let's have an example. So let's consider these two reactions. A plus B gives C plus D. And another reaction, I should have labeled this A1B1 gives C1 plus D1. This is two different reactions. So let's do A1 plus B1 gives C1 plus D1 in there, okay? Always whenever you want to draw an energy diagram, an energy diagram is simply a plot of the energy of the reaction versus the progress of the reaction over time. So how the reaction progresses over time. So the time is going to be in the x-axis and the energy of the reaction is going to be in the y-axis. You start your reaction from the reactants. So what are the reactants? So for both of those, or the A plus B, A plus B. Here in this case, both of them, they have the same energy. So I'm starting with my reactants A plus B and A plus B1. So let's put A1 plus B1 in there, okay? So for the first reaction, the A plus B react with each other and they reach a maximum energy. They reach a maximum energy. And here we're expecting that A and B are colliding with each other, okay? So they reach a maximum energy in there where A and B are going to collide with each other and bonds are going to start to vibrate between A and B. So bonds are going to start to vibrate and bonds are going to start to be broken in this case. This is called the transition state. This is called the transition state, which is the highest energy in a chemical reaction. We call it TS. This is the highest energy in the chemical reaction. It's called a transition state there. The difference between the reactants, the reactant energy and the transition state, this is called the activation energy. And the activation energy, this is the minimum energy required for the reaction to happen. So that is called EA. And activation energy, this is the minimum energy required for the reaction to happen. So it gives me information of what is the energy of the reaction. So the energy of my first reaction is between the transition state and my reactant. So it's this distance over here. And simply you can read it from this graph in there. It tells you what's the activation energy. Okay? So that's the activation energy. Now for the second reaction, it's a transition state is here. This is the maximum potential energy, the maximum energy of the reaction. So this is the transition state for the second reaction. So to measure its activation energy, it's between the transition state and its reactant. So that is going to be EA. Let's label this EA1. Let's label this EA2 in there. Okay? And then after the transition state, after the bonds start vibrating, they start stretching. So the bonds, they are going to start stretching, they're going to get broken, and then a reaction is going to happen and you're going to form your product in there, which is C plus D. And this is C plus D and C1 plus D1 since they have the same energy in there. Okay, so that is considered to be activation energy. So this is how you measure the activation energy. It's the distance between the reactants and the transition state. Now, if I want to compare between both of these activation energies in there, I can get information about the speed of the reaction. And this is how the rule says, if as the activation energy decreases, okay, this means that the reaction becomes faster. So the faster is the reaction. So if I want to compare between those two reactions, this activation energy is less than this activation energy. So I would say that this reaction is a faster reaction because its activation energy is lower, or it is less than the other reaction that has a higher activation energy. We can have an example over here of an ordinary kitchen match. This provides a good example of these concepts. The reactants in the match had basically, or the reactant in the match head, this is stable until the match is rubbed on a rough surface. Okay, so once the match is rubbed on a rough surface, the energy of the rubbing is going to provide the necessary activation energy to cause the match head components to react, and the match is going to ignite. Now, once it's ignited, the reaction now is happening, So since the reaction is happening, the match is going to continue to burn spontaneously until all the fuel of the match has reacted with the oxygen in the air. So this is a good example of a chemical reaction and how the reaction happens spontaneously. For the energy diagram of the reaction. So the energy diagram of the reaction gives us information about the reaction. And as I said, it is the plot of the energy of the reaction versus the progress of the reaction over time. So how the reaction is progressed over time. It always starts with the reactants and it ends up in the products. So it starts with the reactants and it ends up in the products in there. The distance between the reactants and the highest point, as we mentioned, and the highest point or highest energy in the reaction, that is called the activation energy, which is EA. I can compare different reactions with each other, but I need to see different energy diagrams for these reactions to be able to compare their activation energy and see which one occurs at a faster rate than the other. So we set the rules that the lower the activation energy, the faster is the reaction. This is always the case. Okay, so the lower the activation energy, the faster is the reaction. Now, if you look at the energy diagram, you guys, the distance between the reactants and the products, this is called the energy of the reaction. So this is called the energy of the reaction. And remember, what did we say about the energy of the reaction? This is delta H, which is the enthalpy of the reaction. Okay, this is the enthalpy of the reaction. So right now, I can see that the enthalpy is negative. Your products has a lower energy than the reactants, and this is what you need for a spontaneous reaction. You always need the energy of your product. So this is B plus C. You always, I'm sorry, this is C plus D, not B plus C. So that is C plus D. So you always need the energy of your product to be lower than that of your reactants. How am I measuring the energy? I'm just extrapolating in there and measuring the energy. So this is the enthalpy of the reaction. To measure the enthalpy, you look at your reactants, you look at your product, you measure the distance between them. And your enthalpy here is negative. So this is a sign that the reaction is going to be a spontaneous, and it is an exothermic reaction, because we know in exothermic reaction, the enthalpy is going to be negative. So this is an exothermic reaction. So looking at the exothermic reaction there, you have your reactants, you have your products, so measure the distance between them, and this is going to be delta H. Delta H here is negative, so I would say that this is an exothermic reaction. It is a spontaneous reaction. Now for the endothermic reaction. For endothermic reaction, the reactants are lower in energy than that of the products. So see, here the products are high in energy. So they are high in energy. And this is going to cause the change in the energy of the reaction. This is the change in the energy of the reaction, which is delta H, to be positive. This is the enthalpy of the reaction. It's positive. So when delta H is positive, I would say that this one is going to be a non-spontaneous reaction. Okay, a non-spontaneous reaction requires energy, so it basically absorbs energy, absorbs heat. So it's a non-spontaneous reaction. So I would say that this one is an endothermic reaction. So you guys, to sum up, I can get from the energy diagram information about how fast my reaction is by measuring the activation energy. But I would need to compare multiple reactions with each other to know their activation energies, though. So if I have just one reaction with one activation energy, that tells me nothing. I need to see multiple reactions. So see here, this is the activation energy for one. This is the activation energy. Actually, the activation energy is between the reactants and the transition state. So the activation energy is all of that. This is EA. This is the activation energy for the endothermic reaction. So if I compare between those two, this one is going to be a faster reaction. This one is going to be a slower reaction because the activation energy is very high in the endothermic reaction. Guys, activation energy again is the distance between the reactants and the highest point or the highest energy in the energy diagram. So that is for the activation energy. It gives me the speed of the reaction. Another thing that I can look for in the energy diagram is the energy of the reaction. In the energy of the reaction, now I need to take the difference between the reactants and the products. So if the energy of the reaction is negative, then I would say this is an exothermic reaction. Memorize this. Exothermic reaction means the products, they have low energy. So the products, they have low energy. And this is the definition of stable product. A stable product is a product with a low energy. And an endothermic reaction is a reaction where the distance between the reactants and the product is positive. Delta H is positive. So that is an endothermic reaction. And you can see here that the product has a high energy. So when the product has a high energy, I would say that the product is not stable. Okay, so this one is a not stable product versus product with a low energy. It is a stable product. So when I'm talking about activation energies, as I mentioned, to measure the activation energy, you need to have two or more reactions so that you can compare them with each other. So for these two reactions in there, I can see that this one is a low activation energy. So to compare, definitely this reaction is going to happen faster. So when I'm talking about the speed of the reaction, I need to look at the activation energy and check. The lower the activation energy, so the lower the EA implies the faster is the reaction. So if I'm looking at this reaction, this one is a faster reaction for sure. And this one, this is its activation energy here. It's the distance between those two. And this is going to be a high activation energy, so it's going to be a slower reaction. Okay. Now, if I am looking at both of these energy diagrams, both of them are exothermic reactions. Both of them are exothermic reactions. Why? Because both of them have their products lower in energy than that of the reactants. So this product here is lower in energy than the reactant. This product here lower in energy than the reactant. However, you guys, take a look at the energy at delta H. So here delta H is very high. The delta H here is very high. It is negative. Always delta H is negative. So I look at the 720 and it's telling me over here that the change in the energy, the system, gives 720 kilocalories in order to go from the reactants to the products. while as here the system gives 71 kilocalories heat in order to go from the reactants to the products. So I would say that this reaction is a slow reaction, and the heat that is liberated is a low heat, versus this one is a fast reaction, and the heat that is liberated is going to be a high heat of the reaction. High heat of the reaction because delta H here is minus 720 kilocalories. You ignore the negative sign, always you ignore the negative sign, you guys, and just look at the value of the energy, because delta H negative is always exothermic reaction. So here all I'm saying is that this is an exothermic reaction, but the energy is 720 kilocalories, versus here the delta H of this reaction is negative 71 kilocalories. So here it's giving off 71 kilocalories, versus here the reaction is giving off 720 kilocalories, which is a high heat in the reaction. So to look at the heat of the reaction, you need to look at the enthalpy of the reaction, at the delta H of the reaction. And always, if I want to look at the stability for these two, so if I want to compare which one of these is more stable, okay, the one which is more stable is the one that liberates less heat. So the one that liberates less heat is this guy over here. It's the 71 kilocalories and not the 720. So I would say that this reaction here is a more stable reaction. So it's a more stable reaction, okay? It occurs slower. It needs more time. This means that it needs more time to form the product. However, once the product is formed, the amount of energy that is needed to make this product is less. It's way less than the amount of energy that is needed to make the P4O10. So I would say that this one is a more stable reaction, and this one is going to be a less stable reaction. Less stable because the amount of energy that is required to form the product is higher. So the higher the energy, the less stable is the product. The lower is the lower the energy, the more stable is the product. The last section in this unit are catalysts. So what are these? Catalysts are substances that we use normally to speed up the chemical reaction. So we throw in a chemical reaction, and the catalyst, they speed up the chemical reaction, so they have to work with the activation energy to speed it up. So they speed up the chemical reaction, and at the end you generate the catalyst back. So the catalyst needs to show in the product, okay? So whenever you have a catalyst, whenever you see a catalyst in the reaction, this means that the catalyst is going to speed the reaction. Let's have an example of two reactions here. One with one that has no catalyst, and the other one that has a catalyst. So the dotted one is the one with no catalyst. So we say that it is an uncatalyzed activation energy. Uncatalyzed, this means that I did not add in a catalyst. So if I did not add in a catalyst, then I'm going to end up getting an activation energy here. This is the activation energy. I'm just going to call it EA1. Okay, that is the activation energy in there. Now, once I throw in a catalyst, what does the catalyst do? The catalyst reacts with the reactants, and it tries to speed up the reaction. So if it speeds up the reaction, it's normal that the activation energy now is going to be less. So that is going to be EA2. So EA2 is going to be less than EA1 in there. And that tells me that this reaction over here is a catalyzed reaction. It's the same reactants in there, but and because I'm getting the same product, it's the same reactants, but one without a catalyst, one with a catalyst. So the one without a catalyst is going to be a faster reaction. So the question is, the catalyst in there, does the catalyst affect the rate of the reaction? Yes, it does affect the rate of the reaction. So catalysts, they do affect the rate of the reaction. Catalyst makes the reaction faster. When we talk about rate is how fast the reaction is. So catalysts, they affect, so catalysts affects the rate of the reaction, the rate of the reaction, and catalyst makes the reaction faster. So what other factors affect the rate of the reaction other than the catalyst? It's the temperature and the concentration. This is time, okay? So if you look at the rate equation, it's a change in the concentration versus time. So if I increase the concentration of the reactants, the rate is going to increase. So the rate depends on two things other than the catalyst. The rate depends on the concentration of the reactants. Okay, so let's put that. So the factors that affect the rate of the reaction is the concentration of the reactants. Because if you put it in this equation, as the concentration increases, as the rate increases, because the rate and the concentration are proportional to each other. So as the concentration of the reactants increase, as the rate increases, this is one factor that affects the rate of the reaction. Another factor is the catalyst. As we increase, or as we have a catalyst in the reaction, the rate of the reaction is going to increase. This means that speed of the reaction is going to increase. A third factor is the temperature of the reaction. So the temperature of the reaction, as the temperature increases, as the rate increases. So let's say if you have a reaction at 0 degrees, I am not going to expect that the rate of the reaction at 0 degrees is going to proceed in the same speed as the rate of a reaction, let's say, at 40 degrees. So as you increase the temperature, the molecules are going to react faster, so the rate is going to increase, and that will speed up the process to get to the product faster.